Now let us switch gears and enter stoichiometry, which is calculations. Those are just calculations that involve more ratios. So we'll be discussing different manipulations of numbers, converting the mass of reactants to mass of products, or moles of reactants to moles of products, and so on and so on. So the learning objective here is determining the amounts of reactants and products. Could be products formed, reactants consumed, reactants left over, and such. So in summary, usually you might, or you will, I should say, you always start with a given grams of reactant. Okay. And the grams of reactant are useless for us in calculations until we convert them to moles of reactant. So here, that's the grams of reactant converted to moles of reactant. So this is 1, this is box 2. And then from the moles of reactant, using mole ratios, because chemicals react in simple whole number ratios, we can find, using a conversion factor, the moles of products. Sometimes you're just asked to find the moles of products, and that will going to get you to this step. That will get you to box number 3, or you go all the way to find the grams, the weight of products. Gets you to box number 4, which is this. So to get from grams of reactant to moles of reactant, you're just gonna use the molar mass relationship. And then to get from moles of reactant to moles of product, you use the reacting ratio. Okay, so for example, this is the last balanced equation that we balanced. If I know that I have 3 moles of oxygen reacting to give me 2 moles of my product, this is my reactant, this is my product, my conversion factor going to the product will be 2 moles of my product is always created from 3 moles of my reactant, which is what this is saying. Use mole ratios of A and B. So this is A, this is B. In this case, it's 2 to 3, product to reactant, or 3 to 2, reactant to product. So use mole ratios of A to B, or R to P, reactant to product, from balanced equation. You'll get here. And then from here, you just use the molar mass of your compound. You'll find the molar mass of aluminum oxide and multiply that by the number of moles. You're going to get the mass of product. So that's how we're going to proceed in this type of calculations. So let's look at an example. The food we eat is degraded or broken down or digested or metabolized in our body to provide energy for growth and function. In biochemistry I teach, I say that is energy in form of ATP, adenosine triphosphate. A general overall equation for this very complex process, metabolism, represents the degradation of glucose. The formula of glucose is given here. You have 6 carbons, 12 hydrogens, and 6 oxygens. So you're breaking down your glucose to form CO2 that's going to be exhaled, breathe it out, and water that you could sweat it out or pee. So the process is shown down here of how glucose is broken down to CO2 and water. On the right, you're looking at the general ball and stick representation of glucose. The organic molecule, remember, is C6H12O6. So the glucose, in this case, is shown to react with oxygen, kind of a burning process to give you carbon dioxide and water, and you'll check to make sure it's balanced. I see the equation is balanced. I have 6 carbons, 6 carbons. I always like to check. I have 12 hydrogens on the left. I have 12 hydrogens on the right. here I have 12 oxygens plus 6 oxygens gives me 18 oxygens. Here I have 12 oxygens added to the 6 oxygens gives me 18. Everything is balanced. So the equation is C6H12O6 plus 6O2 to give you 6 CO2 plus 6 water. You always have to inspect and make sure it's balanced. So here comes the equation. If 856 grams of glucose is consumed by a person over a certain period, what is the mass of CO2 produced? So my strategy here, as always, is write the chemical equation, but again, I'll have to list my given. So what I'm given here is going to be the mass of the glucose. I'm not given the molar mass. That I have to find. Mass of glucose is given as 856 grams of what the person ate. Okay, and the big question here, the $1 million question here, I need the mass of CO2 produced from the body system of this person. Okay, so this is my balanced equation. I checked it already. Okay, so my strategy here, I'm going to move from grams of my glucose. I'll convert it to moles of my glucose, and then I'll convert that to moles of CO2. Remember, the moles are usually the unifying factor, which means you have to go through the moles of the reactant. This is a reactant, that's a reactant, to moles of the product before you can get to mass of the product. Okay. In between here, we're going to be using conversion factors. Conversion factor 1, conversion factor 2, conversion factor 3. I prefer to use the method of dimension analysis. Now, before I work out anything, let me just go ahead and find the molar masses. Okay. So the molar mass of our glucose C6H12O6 is not given, but I need it. In order to find the moles of glucose, I'll need it. Similarly, I'll need to find the molar mass of CO2. So I know that I have 6 carbons. I know I have 12 hydrogens, and I have 6 oxygens. I've memorized the mass of carbon to be 12.01 about. The mass of hydrogen is about 1.008. And the mass of 6 oxygens, the mass of each oxygen is roughly 16. Let me just use 16 instead of 15.999. This is going to give me grams per mole of glucose. Now let's do all this math. Let's see what we get. Okay, so parentheses, 6 times 12.01. Okay, and then I add that to parentheses, 12 times 1.008. And then I add that to parentheses, 6 times 16. So 156 grams per mole. That is the grams per mole of our glucose. That's the molar mass, molecular mass of our glucose. Now let's do the same and find the molar mass of CO2. Okay, I have 1 carbon, yet I have 2 oxygens. Okay, each carbon is 12.01. Each oxygen is roughly 16. This is going to give me the molar mass of carbon dioxide. And this is just 44.01 grams per mole of CO2. Beautiful. Now that I have those done, I can come back to my dimension analysis. So I'll take my 856 grams of my glucose, C6H12O6, and convert these to moles using my conversion factor 1. What is my conversion factor 1? Conversion factors, remember, they are used to help you to convert SI units from one SI unit to another SI unit. So I know that 1 mole of glucose is equivalent to my molar mass, which is 180.156 grams. See, mole per gram. So I need the mole as the numerator so that I go to the moles of glucose according to my plan. This is our strategy, or our plan strategy. Okay, then I need to move to my second conversion factor. I need to move from moles of glucose to moles of CO2. So I will need my CF2, conversion factor 2. That one you'll have to go back to the equation. Compare the leading coefficients. So 1 mole of glucose reacts with oxygen to give you 6 moles of CO2. I'm going to ask the CO2 because that's what the question is asking about. Okay, so I'll just focus on that. If I was asked about water, I'll focus on the 6 moles of water. If I was asked about the oxygen, I'll focus on the 6 moles of oxygen, so 1 to 6. But here is the relationship between the glucose and the CO2. So 6 moles of CO2 seem to be produced from the balanced equation from 1 mole of my glucose, my carbohydrate, my monosaccharide, we call it carbohydrate. I'm not done. Why? Because if I stop here, my answer is going to be in moles. Check this out. Grams of glucose will cancel. So this is grams of glucose. They will cancel. And then, let me take another color. So moles of glucose and moles of glucose will cancel. So what I'm left with is moles of CO2. If I was to punch numbers in the calculator, I'll get an answer number value, but the SI unit will be moles of CO2. The question is asking, what is the mass of CO2? So we need another conversion factor. And the next conversion factor will use the molar mass of CO2. That's already a conversion factor. So I'll put the mass in grams of CO2 as the numerator because that's where I'm going. That number 44.01 is equivalent to 1 mole of CO2. So mole of CO2 and mole of CO2 gone. Our SI unit of our final answer will read grams of CO2, which is what's being asked here. This process of calculation is called dimension analysis. Otherwise, in the notes, you would do it stepwise, but I find it easier when you write it as a sentence here so that you see your units canceling to the end and it saves you time. So let's punch in these numbers. So I have 856. Okay, move my calculator. Yeah, that's 856. I'm going to divide it by molar mass, my molar mass of CO2. So 856 divided by 180.156. I believe that's what we got right here. I say equals to, multiply by 6. So I'm here at CF2, conversion factor 2, multiplied by 44.01. Okay, so I'm getting 1,254.67. So 1,254.67 grams of CO2. Now remember, our problem has 3 significant figures, so I'm looking at these 5 here. I can write this to scientific notation. 1, 2, 3 steps to the left. So it's 1.25. The 4 is less than 5, so all of the rest of the numbers will be ignored. So 1.25 times 10 to the power positive 3, because I'm going to the left, grams of CO2. Yeah. So our final answer, if this person ingested 856 grams of glucose, after the glucose was metabolized, he released 1.25 times 10 to the power 3 grams of CO2. Okay, so you see, chemistry can explain biology. And that's how you answer that problem. I believe we are correct. So the process we just went through is what is shown here in the slide. And yeah, that is the final answer that we got, and we are right. Now next we're going to look at another example, example 3.14. All alkali metals react with water to form or produce hydrogen gas and the corresponding alkali metal hydroxide. A typical reaction is that between lithium and water, but you can do the same thing with sodium. So sodium can also do it, because if you react sodium and water, you are going to get sodium hydroxide and hydrogen gas. You'll see bubbles. And if it's a lot of sodium, solid sodium, a fire will start. To balance this off, we'll put 2 here and put 2 there. Of course, balance the sodium first, put 2 here and put 2 here. Balance everything. Just follow the process I showed you. Okay, I don't want to explain much about balancing. We've talked about that. So hydrogen gas is produced. Now, in this case, we are given a typical reaction between lithium and water, and that's what you're going to use for calculation. You check the reaction is balanced, still we are getting that hydrogen gas, and you would confirm it's hydrogen gas because when you put there a burning lint, not a glowing one with a flame, it's gonna burns with a pop sound. So burns with pop sound, like pop, pop. And if it's a lot of hydrogen gas, you know what that means. It's gonna be a bomb. So here comes the question right here. Based on this balanced chemical equation, how many grams of lithium are needed to produce 9.89 grams of hydrogen gas? Okay, you're looking at a reaction here, and you're seeing the bubbles, that is hydrogen gas being produced. So in this case, we are told that suppose we have 9.89 grams of hydrogen gas produced, how much of lithium was used in this reaction? Okay. So we are going to do the math backwards, because this time we have information. We have a lot of information about our product, but we don't have much information about our reactant. Before, we were given the amount of glucose, finding the amount of CO2. Now we are given amount of product, hydrogen gas, finding the amount of lithium, the reactant. Let's follow the process. So the very first thing, again, I insist, is to make sure that our equation is balanced, the chemical reaction is balanced. We checked it's balanced. So based on this chemical reaction, how many grams of lithium are needed to produce 9.98 grams of hydrogen gas? Given, we are given mass of product, which happens to be hydrogen gas, and is given as 9.89 grams of hydrogen gas. Needed, we need mass of lithium. What is lithium? Lithium is our reacting material, is our reactant. So strategy. The plan will be, we have to move from grams of hydrogen gas, of course going to the unifying SI unit, which is moles, take it to moles of hydrogen gas, and then from moles of hydrogen gas, we can take it to moles of our lithium, and then from moles of our lithium, we can take it now to the grams of lithium, our reactant. That's the process. You see, when you have a plan, even when you want to build a house, you want to get married, you have to make a plan. If you don't make a plan, it's a failed marriage. If you don't make a plan, the house will come down tumbling. Financial plan, you have to budget. So it's the same thing here in chemistry. We are budgeting. We are planning, we are strategizing. So you always go from the given to the needed. That's how your plan will be, but we always go through transit. We transit through the moles. All right, so we'll need a conversion factor 1, conversion factor 2, conversion factor 3, and we again are going to use the method of dimension analysis. Okay, so now I know that the atomic mass of lithium is what? Let's look at the periodic table. Atomic mass of lithium, main group 1 is 6.94. So I'm going to list it here, 6.94 grams per mole of lithium. And then we are dealing with the molecule. So the molecular mass of hydrogen, which we know has 2 hydrogens, is going to be 1.008 times 2. Where did I get that? Again, from the periodic table right here. 1.008 is the atomic mass of hydrogen. So this is going to give us 2.016 grams per mole of a molecule of hydrogen gas. And now back to our plan. The given mass of hydrogen gas produced is 9.89 grams of hydrogen gas. I need my first conversion factor, CF1. From grams to moles, I'll say the mole should be the numerator because that's where I'm going. We know the molar mass of hydrogen gas is 2.016 grams of H2. Doing so, this unit and this SI unit will cancel out. Our answer will read moles of hydrogen gas. But that's not what we need. We have to go up to grams of lithium. So I'm going to need my second conversion factor, this right here. I need to go from moles of hydrogen gas to moles of lithium. And in that case, I'm going to compare the reacting ratio of hydrogen gas and lithium in the balanced chemical equation. So there's only 1 mole of hydrogen gas here, and there's 2 moles of lithium. So since I'm going towards the lithium, I'll say for every 2 moles of lithium, we will produce 1 mole of hydrogen gas. And why do we need to do that? So that the SI units will cancel. Moles of lithium is the numerator because that's where we are going. And then from here, we're going to go to the third conversion factor. This is conversion factor 2. So now we go to conversion factor 3. I'm going from moles of lithium to grams of lithium. I will need the atomic mass relationship to a mole. And I see that 6.94 grams of lithium is always equivalent to 1 mole of lithium. Now, why do we do that? We do this so that the SI units will cancel out and we are left with grams of lithium. That's how you know that you did it right. The question is asking how many grams of lithium are needed. So that's where we are landing. I'm good. So I need to punch in the numbers here. Bring the calculator. Move him somewhere here. I'll move it back when needed. So 9.89 divided by 2.016 equals to, multiplied by 2 equals to, and then I'll need to multiply that by 6.94 equals to, so I'm getting 68.092 grams of lithium will be produced. Now I see I have 3 significant figures, so 3 will land here, so it's 68.1 because 9 is greater than 5, so we'll round up the 0 to 1. So 68.1 grams of lithium will be needed as a reagent to produce the said 9.89 grams of hydrogen gas. 9.89 grams of hydrogen gas. And that is our answer, my friend. And yeah, so the setup we used is exactly what you're looking at here. Is the method of dimension analysis. We are correct.